Welcome to Brain Vision.
For part A of this question, to calculate the energy of the photon, we're going to consider the longest wavelength, which has the initial state of n equals 3, and then the final state we're told is n equals 2. So to calculate this energy, we're going to use the equation that says that the energy, which we're going to call E, is equal to 13.6 electron volts, which comes from the ground state energy of the hydrogen atom, multiplied by the difference between the final state, which is 1 over 2 squared, minus the initial state, 1 over 3 squared. So carrying out this operation gives us our energy value of the photon. Plugging these values in and carrying this out, we find that this is equal to 1.89 electron volts. So now that we know the energy, we can calculate the wavelength. Since the energy and wavelength are related by the equation E is equal to hc over lambda, we know that lambda, then, the wavelength, is equal to hc over E. So lambda is equal to h. Here h is Planck's constant. And we want to use the electron volt version of Planck's constant since our energy is in electron volts. Plugging these values in, c is also, of course, the speed of light. We find that this is equal to 658 times 10 to the minus 9 meters, or 658 nanometers. You can use meters or nanometers. I'm going to choose to use nanometers here, but you could also write it as 10 to the minus 9 meters, which would be correct as well. For part C, it wants the photon energy, which gives us the shortest wavelength in the transition from the figure. Okay. So the shortest wavelength, again, we have the same equation, but this time it's coming from n equal to infinity. So the shortest wavelength comes from n equals infinity. So we have 13.6 electron volts. Let me rewrite that. We have 1 over 2 squared, so our final state is still n equals 2. And our initial state is infinity, so we're subtracting 1 over infinity. And you could square infinity, but infinity squared is still infinity, so this is just 1 over infinity. But 1 over infinity is equal to 0. So this value here goes to 0. Carrying out this operation, we find that this is equal to 3.4 electron volts. We can box this in as the solution for C. For D, it wants us to find the wavelength. So we're going to, again, use the exact same equation as we did in part B to find the wavelength. So lambda is equal to hc over E. Again, h is in units of electron volt seconds, so 4.1357 times 10 to the minus 15 electron volt seconds. And c is still the speed of light in units of meters per second. Carrying out this operation, we find that this wavelength is equal to 365 times 10 to the minus 9 meters, or 365 nanometers. Wavelength is often given in units of nanometers, so it's convenient to write it in units of nanometers for easy comparison. And then lastly, part E says, what is the shortest possible wavelength in the Balmer series? Well, the Balmer series is going from some higher value down to n equals 2. And so that means we found the shortest possible wavelength in the Balmer series. It's the wavelength that was given in part D. So the shortest possible wavelength in the Balmer series is just simply 365 nanometers. We can box that in as our solution to E.